Inside every intelligent machine lies a hidden brain, a marvel of engineering smaller than a fingernail, yet more complex than a city. This is the AI chip, and while it is invisible to the naked eye, it is quietly controlling the infrastructure of our modern world. But what makes it different from the computer chips we've used for decades? The secret lies in how it thinks. Traditional processors are linear calculators. AI chips are designed to mimic the human brain, processing billions of calculations simultaneously. The journey of an AI chip begins in the most humble of places, sand. From this, we extract pure silicon. This silicon is melted and grown into a single, perfect crystal ingot, which is then sliced into wafers thinner than a sheet of paper. These wafers enter the fab, a factory cleaner than a hospital operating room, where a single speck of dust could destroy a billion-dollar batch. Here, the most complex machines ever built by humanity take over. Extreme ultraviolet lithography. They blast molten tin with lasers to create light so intense it can etch transistors just a few atoms wide onto the silicon surface. Layer by layer, billions of transistors are stacked, creating a 3D labyrinth of electrical pathways. To understand the scale, imagine fitting the entire road network of the planet onto your thumbnail. That is the density of an AI chip. Once etched, the wafer is sliced with diamond sauce. The functional chips are packaged, ready to connect to the world. Thousands of these chips are linked together in supercomputers, working as a single mind to train the large language models we use today. They process visual data in milliseconds, allowing autonomous vehicles to see and react faster than any human driver. In healthcare, they scan DNA sequences and discover new drugs, condensing decades of research into days. The cost of entry is staggering. A single factory costs $20 billion. But the cost of being left behind is even higher. We have built sand into intelligence. This tiny chip is not just hardware. It is the foundation of our next evolution. It begins not with metal, but with imagination. In the design labs of NVIDIA, Apple, and Google, architects map out digital cities billions of transistors strong. The raw material is humble, common sand, purified, melted, and spun into a single, perfect crystal. It is sliced into wafers, the blank canvas of the digital age. Enter the clean room. Cleaner than an operating theater, here in the realm of the nanometer, a speck of dust is a catastrophe. We are building at scales smaller than a strand of DNA. The lithography machine awakens. Using extreme ultraviolet light, it etches patterns of impossible complexity. Layer upon layer, a skyscraper of circuitry is built, atom by atom. Humans supervise, but robots rule this floor. Automated arms move with surgical precision, carrying the precious cargo between chemical baths and furnaces. Finally, the wafer is diced. The fragile silicon brain is encased, given its protective shell and the gold connectors that will link it to the world. But before it wakes up, it must be proven. Subjected to extreme heat and massive AI workloads, only the flawless survive to power the artificial minds of tomorrow. To understand the future, we must look inside the engine driving it. The AI chip is not merely a faster processor. It is a fundamental reimagining of computation. Traditional CPUs are like master scholars, solving difficult problems one by one. But AI chips? They are armies. They utilize massive parallel processing to handle billions of variables simultaneously. This architecture is critical. Training a modern large language model requires months of continuous calculation across tens of thousands of these chips, consuming the energy of a small city. Creating these marvels is the most complex engineering feat in human history. A modern fabrication plant costs over $20 billion, more than the GDP of many nations. It relies on machines that blast molten tin with lasers to etch transistors smaller than a strand of DNA. A process so precise, it borders on magic. The supply chain is a fragile global web. Designs originate in the United States, utilizing lithography from Europe to be manufactured in the foundries of Taiwan and South Korea. In this arena, giants like NVIDIA, Intel, and AMD battle for supremacy, while TSMC remains the silent forge upon which the entire digital world rests. But we are hitting walls. The heat generated by these dense clusters is immense. We are fighting the laws of thermodynamics and the physical limits of the silicon atom itself. Consider the human brain. It outperforms supercomputers in general intelligence while running on the energy equivalent of a dim light bulb. Silicon is fast, but it is brutally inefficient. The future, therefore, may not be just smaller chips, but different ones. Neuromorphic architectures that mimic biological synapses and quantum processors that solve problems linear computers cannot touch. This technology is now the world's most valuable resource. Control over the chip supply chain has become the defining geopolitical struggle of the 21st century. As these chips enable true automation, they will rewrite the social contract of labor. Factories, offices, and economies will transform faster than we may be ready for. We are building a new form of intelligence. The question is no longer if it will change our world, but whether we will recognize the world it creates.